Hello everyone, this is Brandon with the video question line, GD&TBasics.com. Today's topic is tolerance stacks, chain dimensioning versus baseline. The question that we have here today is from Tyler, and it says, I have started a new job as an engineer and one of my primary roles is creating drawings. I keep getting drawings rejected because I'm using chain dimensioning and have been told that it is a forbidden type of dimensioning. Can you tell me why this is and why ASME still supports it? So real quick, Tyler, before we get into this, it's not forbidden. We often do tell, especially new engineers, new draftsmen, new designers, to avoid it unless it is functionally acceptable. And typically it's not, because we have parts that align to other parts. And these chain dimensions, the features need to be aligned to some sort of rail, or in the world of GD&T, to a datum reference frame. When we do chain dimensioning, it's going to be from feature to feature. So we start getting all of these tolerance stacks, and I would assume that's why your drawings are getting rejected, is because of the tolerance stacks. But we can go ahead and take a look at this, and I've put a little scenario in here. If you look at these up at the top, I'm showing just a simple bus bar. It's a copper plate, and notice how we've got a rail coming around here. So this is the two rails, sorry. So this copper bus bar is going to go into this assembly. So any kind of drawing we ever make, we need to look at the assembly requirements, or the function of the component, to fully determine how we need to dimension the part. So let's say that this was your part here. This is you're going to do a drawing for this copper bus bar here. And we look at the assembly and we see that it's going to come in, slide up against here and here. Well, if we did this as chain dimensioning, I mean, most any type of tolerancing that we're going to do, we're going to wind up with this scenario over here where if it's chain dimensioning going from here to this hole and then from that hole to here all the way down, there's going to be a tolerance stack, and we're going to look at that in just a second. But it's going to take, as we get to each hole going further down, because this is really our origin here. So this is the corner that it's going to lock to. As we get further away from that corner, the scenario is going to get worse. Those holes are going to be even further off. They are showing up here that there's 2 bolts going into the first 2 holes and 2 bolts here going into the last 2 holes. Not sure what's going into the center of that, which doesn't really matter at this point. We could assume that they're going to transfer drill or something on this, put in all these other holes. And at that point, it really, the through hole is just going to align to the hole that's there in the copper bus bar. But that part of it is irrelevant at this point. Let's just look at the first 2 holes and the last 2 holes. So from our course here, we have this, it's in the Engineering Drawing Basics course. You may have seen this already, but we have a really nice lesson in there that really goes into a lot more detail than what I'm going to go into here. But we're going to touch on it and just to get your question answered here. Okay, so on this drawing here, you can see this is a classic case of chain dimensioning. Look at the drawing itself. Now we have 18 holes here, and they're 5/8 in diameter. So we have 18 holes, 5/8 in diameter. We would have to assume at this point, based off this drawing, that this will not be a 5/8 bolt going through here, because our maximum material condition for the size of the hole would be 615. And we know that by looking down here, we've got a 2-place decimal, or that's a 3-place. So actually this would be 620. So we've got 5 thousandths there. So that would be, because it is a 3 decimal place, we've got plus or minus 5. So the MMC of this is going to be 625. Remember, whether we're talking about GD&T or coordinate dimensioning, for these features, we still have our maximum material conditions and our least material conditions, or upper limits, lower limits. So we have these 18 holes. Based off of the dimensions up here at the top, we're going to use this one right here. So look at this hole. And it's chained all the way down, meaning it's from one feature to the next to the next. So just coming from right here to this first hole, it's a 2 decimal place value. So for that one there, we have plus or minus 10 thousandths. Okay, so for the first hole here, that very first hole can either shift, and I'm going to call this direction here X. So this is X. So it can shift an X 10 thousandths forward, so 1.760, or 10 thousandths back, so 1.740. So if you look at that one right there, remember we've got a 615 or a 620 hole. So now that 620 hole can be 10 thousandths out of position or location in X, both directions. Now this is also, if it's stacking from here too. So this 3/4 up, going to, because this is in line here. So that 3/4 inch dimension, or the 0.75, that can be 10 up or 10 down. So that would be the Y direction. So that's 10 up, 10 down. Just from this rail down here, and we showed that's where it goes into the assembly. So from there going up in Y, it can be plus 10, minus 10. But then we have that 1.25 inch, or the 1.25 dimension from there. That's another plus or minus 10. So that's 20 thousandths right there in location that could be off, up or down. So starting off for this hole, the worst case condition that we have for it is that it could be up by 20 thousandths. Okay, so we said that the maximum material condition is 620 based off of the size. So, but we can be shifted up by that as well. So look at how far that can be off. Well, that 20 thousandths up, 20 thousandths down, now we have to account for that. So we're, as far as what we can clear, we would subtract it out of here. So now looking in the up condition, we would be down to 600 thousandths now that we could potentially clear there for this location. And of course, going down, we had the same situation. This could all shift downward as well. It could go down 20. So looking at a perfect location, if this was mating up to a through hole on that bracket that we showed, hopefully that's a clearance hole. And when this drops through, the hole on that part needs to accommodate this. Now go all the way to the opposite end. It just gets worse as we go. So as we go down X, now the good thing is that as far as this location here goes for all the holes, those are all going to be plus or minus 20 on the top 8 holes there, or 9 holes there. Those are all going to be plus 20, minus 20 in location in Y. But in X, it's just going to start to add up and get worse and worse. So coming from this hole, because we are starting here now with the 1.5, we have this listed here 8 times. So because that is plus or minus 10, that's a location for this last hole. It could be in X, this direction, off by 80 thousandths. Or it could go back. It could go back the opposite direction and be minus, going the other way. So we would have to go in and we would have to subtract that 160 away from our maximum material condition in order to know or understand how far this could really be off. And when you get to that last hole, if you're using chain dimensioning, like I said, you're going to have to modify that hole now by 160 from MMC. Well, really what you're going to be doing is adding it to it, because you're going to have to go back and add it to the 5/8, depending on where the design is for what this is supposed to clear. So if we're going to leave the 5/8 and that's going to work for this first hole, we would have to come back in and add 160 thousandths in diameter to all of them in order to get them to work, if we were going to leave them as one pattern. Or we could go back in, as far as design goes, we could go back in and we could start making slots instead of holes. We could do slots either on this part or the mating component, so that no matter what, we're not going to put in all of the slot up and down in Y. We could leave the slot width at the 625, but we would extend this out 80 thousandths both directions and create slot features in there, so that as this tolerance accumulates, if we're going to do it this way, coming from the rail, then we would always be able to clear the bolt. Now, if it really didn't matter, and this is getting back to function, if it really didn't matter whether or not these holes were that far off from each other, meaning that we did have some sort of features in the other one that would be very accommodating. Let's say that by design on here, we showed it up against that rail. But let's say that by design, something is just going to come in, let's say like a terminal ring. This is a bus bar, so it's copper, so this is for conducting electricity in some fashion. So let's say we're just going to mount a terminal ring right here, and possibly one up here, and then one over here, and one over here. But these are cables, so they're very independent of each other, as long as whatever fastener is going through there is able to pass through and connect this terminal to that. Well, then it's not going to matter what its relationship is to these two rails. So then baseline does work for that. I've seen instances where, especially for long parts that don't fit fully inside of the machining center, where they will use baseline dimensioning for it, so that the machinist can just advance from hole to hole, understanding that there's going to be quite a bit of stack tolerance down the 20 or 30 foot length. But they don't care, as long as the relationship of just this one to this hole is good, and then from this hole to this hole, and so on and so forth. Maybe there's actually going to be a slotted tab that goes over this with two holes, but it's only going to be over those two holes. Well, then this relationship has nothing to do with this corner, so it wouldn't matter. But going back to the rail that I showed in the beginning there, where we do have, it is going to fit into a corner. For you, Tyler, if this was your drawing, then you might want to switch to baseline dimensioning. Now on this one here, to the first hole, we still have the stack tolerances that we talked about for this first hole here. We have the 0.75. Sorry, they switched it up on me here a little bit. We have 0.75 for this one here, which is going to be the plus or minus 10. They've came all the way down from the base, or from this rail for this one. So now this hole is only going to be in the Y direction. It's only going to be off plus or minus 0.01, but that's in the Y. Same thing though that goes for the X, or the X over here. We have 1.75, so to the first hole, it's going to be plus or minus 10 thousandths. Now go to the last hole. Again, it's baseline, so all dimensions for X are coming off this back rail here to the left. So on this one here, we have 13.75. It's 2 decimal place, plus or minus 10 thousandths for the location of that one hole. So it can be off in X in either direction by 10 thousandths, and it can be off in Y either direction in 10 thousandths. This creates, if you look at the hole and kind of blow this up and look at it, here's our crosshair there. This creates the square tolerance zone that everybody talks about for coordinate dimensioning. This is the whole reason why we use GD&T, or position tolerancing, for this, is to get a circular one. But this gives us that tolerance value here that is total of 20 thousandths, right? So the overall height of it is 20, from center is 10 thousandths. And then also over here in the X, we have the same thing. We've got a total of 20 thousandths, but from center line, negative 10, positive 10 for both of those. So this is a way to get rid of all of that tolerance stack and limit it down to just this plus or minus 10 thousandths for the location, and clean up your drawing and start reducing the number of rejected drawings that you're getting based off of chain dimensioning. I've been through that quite a bit myself. I've been guilty of it in the past, making drawings that that do have a lot of tolerance stack due to that. So you're not alone there. So let's look at one more scenario here. And I'm bringing this one up, Tyler, because I saw you were also enrolled in the fundamentals course. Haven't made it there yet, but it's brought up in engineering drawing basics. But this is a way to really clean up your drawing and really get more accurate to that assembly, the functional requirement. So on this one here, they've applied GD&T to this one. They're using a position tolerance here, as you can see, for those 18 holes. There's a lot of options we can do with this here at this point, but just looking at it for what it is, they have the bottom surface. In this case, it'd be the top surface of third angle projection. So remember that. So on this one here, that bottom or top surface is A, primary datum. According to this, it's primary. And then B is right here. Now notice that on B, it's in line with this dimension. With it being in line, that means that we have a midplane here. And then now everything will be positioned or located about that, but we could have taken on this datum here, not put it in line with the dimension and just moved it over here. Get it away from that. Remember, anytime it's in line, it's going to treat it as a feature of size datum or midplane datum, sometimes called a width datum also. But we could put it over here to the side. That would mimic what we had in that first drawing where it's here and here. But with position tolerancing, despite how or regardless of how that's done, these cylindrical tolerance zones, in this case it's a diameter of 10, coming from the datum reference frame from ABC, they are perfectly oriented and perfectly located. So with this, we have zero tolerance stack. In those first two examples, those features are being dimensioned, and whether it's chain or baseline, they are coming from the part. It's not telling you to use a datum because there's no datums identified on those. On this one, it is saying measure it from a datum. So now looking at C, even if the part here was cut like this, it's going to engage B and then C, and these measurements are coming from the datum planes, not from any imperfections with the part. So that's why there's zero tolerance stacks with position tolerance for the locations, because it's setting up the perfect datum reference frame, and all of your tolerance zones are perfectly oriented and located, and they're located with the basic dimensions from B and C, but they're perfectly oriented, perfectly located. They cannot move when we're at inspection. Nothing can alter those. The only thing that can be altered with that, this one's at RFS, but right behind the 10,000s here, could put in a maximum material condition modifier, so that if this thing did come in at maximum material condition, we would get 10, but then as we grew, we could get 10,000ths of bonus tolerance added into that. But still, the tolerance zones, the location and orientation of those are perfect. They never change. They never move. So something for you to consider as you get into the fundamentals course and familiarize yourself with position tolerancing. That would be the most accurate and best way to convey it. You can go in and start opening this up a lot, the actual tolerance, and make it still functional, more functional than what the other two would allow for, but be very specific about how it gets inspected and the fact that it's coming from datums. Okay, so I hope that answered everything up for you there, Tyler. For anybody out there, if you do have questions, please send those to us at questions@gdntbasics.com. I know a lot of you are doing it already. That's where we're pulling all these questions from. Don't forget to visit us there at gdntbasics.com. Check out our website. If you're not on our email list, up here at the top, the gdntbasics.com /GD&T or GDT-symbols-chart /. make sure you get on there and subscribe to our email list and get the free wall chart on there. All right, guys, that's it for today. Thank you, and keep a lookout for more videos. Have a good day.